One of the critical skills of organic chemistry is being able to draw accurate structures of organic molecules. And what we're going to talk about in this segment is one way of drawing structures of organic molecules, which is the so-called Lewis structure. A Lewis structure is going to be a representation of the molecule that shows every single bond in the molecule, every single unshared electron pair in the molecule, or unpaired electrons, as well as any formal charges that are present in that molecule or ion. So we're going to be looking at Lewis structures being the most detailed way of going about drawing organic molecules. So Lewis structures are going to show pretty much all the gory detail that we possibly can, with the exception of perhaps information about bond angles and things like that. We're going to show all of the covalent bonds in the molecule, all of the unshared electrons, in other words, all of the lone pair electrons, and all the formal charges. And I'm going to abbreviate throughout the semester formal charges as FC. So it's going to show all FCs, all formal charges. We're going to go through the steps for drawing a Lewis structure for a particular molecule. So one molecule, when we're talking about Lewis structures, you'll typically be given a molecular formula such as C3H8O. And we're going to go through with C3H8O as our example molecule. We're going to go through the steps for drawing a Lewis structure or Lewis structures for this molecule. So C3H8O. And I will warn you from the start here that with organic molecules, typically for any given molecular formula, such as C3H8O, there are very often multiple different Lewis structures that are acceptable. Those different Lewis structures will correspond to what we call different constitutional isomers, molecules that have the same number and type of atoms, but different connections between those atoms to make different so-called constitutional isomers. So we're going to use C3H8O as our example molecule here, and we're going to try to come up with some different possible Lewis structures for that molecule using a series of guidelines. So we're going to go through the guidelines here one by one, and we're going to use C3H8O as our example to illustrate how we use those guidelines. So our guidelines for drawing Lewis structures step by step. And you are reminded here that when we're looking at these videos, the best strategy for this is to take detailed notes of what you're viewing so that you can review those notes later. And by writing things down, it typically helps people to grasp the concepts and remember them later. So we're going to draw the Lewis structures here step by step. And those steps are, first off, we need to determine the total number of valence electrons in the compound. To determine the total number of valence electrons, assuming it's a neutral molecule, what we're going to do is add the valence electrons that correspond to each individual atom in the molecule. And remember that valence electrons are going to correspond to the column of the periodic table that that atom appears in. So first off, determine the total number of valence electrons. So this is how many electrons we will have to work with in drawing in our covalent bonds and our unshared electrons. The number of electrons that correspond to each atom, when we sum that up, have to be the total number of electrons that we see appearing in the Lewis structure for the molecule. So we're going to determine the total number of valence electrons that are present in that compound. And for that, if the molecule is neutral, meaning there's no net formal charge, what we're going to do is add the number of valence electrons from each individual atom. And we will sometimes be drawing Lewis structures for ions, that is, molecules that have a net formal charge. And so if the molecule has a net formal charge, in other words, if it's an ion, if the net charge is not equal to 0, but instead you would see that overall the molecule has a net charge of +1, -1, or whatever else the case might be, then what you'll do is you'll add up the number of valence electrons corresponding to each atom, and then to account for the positive or negative formal charge, a negative formal charge, a net negative formal charge, indicates that there's an extra electron. So you will add 1 electron for every net negative charge. And if instead it's a net positive charge, what you're going to do is subtract 1 electron, because the net positive charge indicates that we are deficient in an electron. So If the molecule is charged, first off, add the number of valence electrons from each atom. Then what you'll do is add +1 electron for every negative charge. So if the net charge is -2, that means you're going to add 2 extra electrons. And on the other hand, if we have a positive formal charge, a positive net charge, then what you're going to do is subtract 1 electron for every positive formal charge. So in other words, if the net charge on the ion is +2, that means that you're going to be subtracting 2 electrons from the overall count. So the overall count is determined by adding up the number of valence electrons from each atom in the molecule. And then if it's a charged molecule, you'll add extra electrons for each negative formal charge. If it's a positive net charge, you'll subtract an electron for each positive formal charge. So that's how we're going to go about determining the number of valence electrons in the compound. Going back to our example, C3H8O, which I'll go ahead and put in blue here. C3H8O, and we see nothing in that formula above about the molecule having a net charge. If the molecule had a net charge, if it was an ion in other words, it would have to be specified in that molecular formula. Like we'd say C3H8O and then superscript negative or superscript positive to indicate a positive or negative net charge. Since none of that's listed here, what we need to go with is this business of determining the number of valence electrons for a neutral molecule. So looking at the periodic table, carbon appears in the 4th column of the periodic table. You can see that in the periodic table that's posted on Canvas by looking at the top above the column that says carbon. You'll see IVB and IVA. That IV is the Roman numeral for 4. We're in the 4th column of the periodic table. And there's 3 carbon atoms. So what we're going to do to determine the number of valence electrons contributed by carbon is take 3 carbon atoms. And each of those carbon atoms contributes 4 electrons because carbon is in the 4th column of the periodic table. And there were 3 carbon atoms in total, so that's how we came up with the 3. Then continuing onward, there are 8 hydrogen atoms, so we'll put 8 there. And each hydrogen atom contributes 1 electron because hydrogen is in the 1st column of the periodic table. And then finally our oxygen atom, there's just 1 oxygen, we'll put 1 there. And then in parentheses here, I'm going to put the number of valence electrons contributed by the oxygen. Looking across the periodic table, oxygen is in column 6. It's listed there as VI for Roman numeral 6 in your periodic table. So we'll go ahead and put that in as 6. Add all that up, and that is going to give us a total of 26 valence electrons that we have to deal with here. So what that means is that our Lewis structure that we draw, since the Lewis structure shows every single covalent bond and every single lone pair electron, that means that our total number of electrons that need to show up in our Lewis structure is 26. So that's what we're going to be aiming for as our goal here, is that the Lewis structure has to contain and explicitly show 26 electrons, because we're showing every single valence electron. So after we determine how many valence electrons there have to be in the compound, that was step 1 of our outline here for determining possible Lewis structures. The second thing that we need to do is determine the arrangement of atoms. In other words, we need to determine which atoms are connected together by covalent bonds. We need to find a way to link all 3 carbons, all 8 hydrogen, and all oxygen atoms, or a single oxygen here in this case, together into a single structure. And typically when we're looking at the arrangement of atoms, which atoms are connected to one another, there are very often going to be multiple possible correct ways that the atoms could be arranged together. And if we were actually working in a lab and trying to determine what the actual connectivity between the atoms is, there would be additional experiments that we would typically do that would allow us to experimentally evaluate which structure was the actual correct structure that the molecule we were looking at possessed. But in this case, when we're just looking at how to draw Lewis structures from the perspective of a molecular formula, what we're going to focus on here are drawing out the different possibilities that could correspond to C3H8O. So in our second step here, what we're going to do, adding point 2 to our list here of drawing out possible structures for organic molecules using these Lewis structures, is we're going to determine possible arrangements of atoms. And we're going to try to be very careful here that each possibility that we show is a different, distinct possibility rather than redrawing the same thing twice. We want to avoid redrawing the same thing twice here. It's a waste of time, and it's just not a very professional way of going about drawing things. We want to make sure that each structure we draw is an actual different chemical entity. So we're going to determine the possible arrangements of atoms. Or in other words, we're determining what atoms are connected to one another in the molecule is what we're determining here as our possibility. As we go about step 2 here, determining the possible arrangements of our different atoms, I'm going to give you one pro tip, and that is we can always determine how many rings there have to be in a particular molecule. That means how many carbon atoms or other atoms form a ring rather than a chain, and how many pi bonds, that is double bonds or triple bonds connecting atoms, that we have to have in a particular molecule. So when we're determining the possible arrangement of atoms, we can automatically determine the number of rings in the molecule plus the number of pi bonds, where a pi bond, examples of that would be 2 carbon atoms connected by a double bond, like so. That set of 2 lines there indicate that I've highlighted in yellow indicates a double covalent bond. And in that double covalent bond, one of those 2 bonds is a so-called sigma bond or a single bond. And the second bond is a pi bond. So one of those 2 bonds, I'll just put it in red, is our pi bond. The other one is a sigma or single bond. And so number of pi bonds here we would define as being 1 pi bond, because one of those 2 bonds is a sigma bond, the other one is a pi bond. Any bond beyond a single bond is defined as a pi bond. So when we're looking at this second structure here, a carbon pair that's connected by 3 bonds, out of those 3 bonds, 2 of those 3 bonds would be defined as being pi bonds. Only the one bond is defined as a sigma bond. The other bonds there will always be defined as pi bonds. So we've got 1 pi bond up top out of that double bond, and on bottom we have 2 pi bonds highlighted in red there. The first bond is a sigma bond. Anything beyond that is a pi bond. And there can also be pi bonds that connect carbon to other atoms, such as a carbon-oxygen double bond. Would be defined as having 1 pi bond, which I've highlighted in red there. And so that's going to be one possibility, is that we have some pi bonds in the molecule. A ring is just going to be defined as atoms that are connected rather than being a chain. It's going to be atoms that are connected into a ring of some sort. So for example, a 5-membered ring, and one of those atoms could possibly be an oxygen atom. So this would be an example on the left here, as I'll highlight, of a ring system. So we can determine how many rings and pi bonds there must be present in a molecule as a way of narrowing down the possible Lewis structures that we need to draw. So this is a really useful shortcut rather than using trial and error to figure out whether you can plug all the atoms into a particular ring or into particular chains, is by using this equation that we're going to show to determine the number of rings and pi bonds straight away. So the equation is, and this is a good equation to commit to memory for future exams and quizzes, 2 times the number of carbons in the molecule plus 2 minus the number of hydrogen atoms that appear in the molecular formula minus the number of halogen atoms, and we abbreviate halogen as X, plus the number of nitrogen atoms that are present in the molecule. And we divide all that by 2, and that's going to give us the number of rings and pi bonds that absolutely have to be present within the molecule that we are looking at. So for the molecular formula C3H8O, which we are using as our example problem throughout here, So for C3H8O, we'll do this calculation of number of rings and pi bonds. And by the way, that's a sum of rings plus pi bonds, meaning that if we end up with a value of 1, it could be 1 ring or 1 pi bond. If we end up with a value of 2, it means there could be 2 rings, there could be 2 pi bonds, there could be 1 ring plus 1 pi bond. It doesn't distinguish between these two types of systems, a ring versus a pi bond. It just tells you how many there have to be of that in total. So for C3HAO, number of rings plus pi bonds, we'll go ahead and do the equation here to get us off on the right start about what types of connections we can put between our atoms. So we'll do 2 times the number of carbons, which is 2 times 3, plus 2, minus the number of hydrogens, which is 8, minus the number of halogens, there's none of those, plus the number of nitrogens, which is 0, divided by 2. You'll notice that oxygen does not play into this equation in any way, shape, or form. It doesn't impact how many rings and pi bonds are allowed, so we leave that out of the equation. So we go ahead and do the math here, and what we end up with in the numerator portion of the equation is, if we look at this, it's going to end up being 0 divided by 2. 0 divided by 2, of course, is 0. And so any correct structure that we can draw here for our molecule, keeping in mind that this equation works for a molecule that has no net formal charge. So it can't work for an ion. It's going to work only for molecules with no net formal charge, which is definitely the situation here for C3H8O. We already established that it was a neutral uncharged molecule. So this C3H8O is going to have no rings or pi bonds. So any correct structure that we draw for this absolutely cannot have any rings, cannot have any pi bonds. So it's going to help us narrow down possible structures that are reasonable for this. When we go onward from there, determining the possible arrangements of atoms that we can draw, what we want to think about are the different possible so-called constitutional isomers, the different ways that we can arrange atoms to make different structures where there are different atoms connected together. So C3H8O, usually when drawing out the possible structures here, when drawing out the different possible arrangements of atoms, what I suggest focusing on first, the first 2 things are, number 1, determine how many rings and pi bonds there are, and number 2, determine the possible connections that you can put between all of the non-hydrogen atoms. So try to figure out all the arrangements of everything except for the hydrogen. So in other words, how can we connect 3 carbons and an oxygen to all the different possible structures? So what we're going to do here is try to make all of the possible connections, or all the possible ways to connect between our non-hydrogen atoms that are present in the molecule. So we're going to make all possible connections between the non-hydrogen atoms in this molecule. The reason that we do it this way is because typically our hydrogens are going to be our filler material at the end that we'll use to help us obtain a complete octet around all of our atoms. Prior to that, when we're thinking about coming up with all the different possible constitutional isomers, all the different ways that the atoms can be arranged, it's usually best to not think too much about hydrogens at that point, because the hydrogens are very much getting down in the weeds, and we want to kind of think about the big picture of what's the overall skeleton of the molecule look like. So to determine that overall skeleton, we're going to focus on the 3 carbons and the oxygen, all the different ways that those could be connected together. So we're going to try to draw out a list here of ways to connect our carbon atoms and our oxygen. So we're going to try to find ways to connect 3 oxygens, which I'll put 3 O's there, and it's 3 carbon atoms, my bad. 3 carbon atoms and 1 oxygen. And the ways that we connect the atoms are using covalent bonds, because we would find that if we looked at the electronegativity difference between these different atoms, certainly they all fall into the realm of covalent bonds rather than ionic. So our goal here is to find all the ways we can connect 3 carbons and 1 oxygen. So thinking about just different possibilities here, and all of our possibilities have to involve no rings and no double bonds or triple bonds, no pi bonds in other words. So possibilities that come to my mind are, we could just string together 3 carbons. We could put an oxygen atom at the end. We could take a carbon, then we could put an oxygen atom in, and then 2 more carbon atoms. That would be another route to go here. We're trying to come up with all the different possibilities. So another possibility would be we could take carbon, 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 and rather than connecting the oxygen at the end as we did in the upper left situation there, we could connect the oxygen to the carbon in the middle. And we try to exhaust all of our different possibilities. And usually the way that is effective for doing that is start with the simplest possibilities first. So in other words, when I was starting with the simplest possibilities, I was starting with these scenarios up top here where all of the carbon atoms and other atoms are just in a straight chain, a line of atoms. And then from there, I start pulling atoms off of the chain to create branches out of them. So for example, creating a situation like this where we've put a branch there of an oxygen atom at carbon number 2 of the chain there, of those 3 carbons. You might also try to do something like, say, a carbon, oxygen, carbon, thinking of that as a possibility, and then a carbon bonded up there as another possible opportunity here. So we'll go ahead and try that out. And what you will find is that there's going to be some trial and error associated with these different structures that we're drawing, where we may get to the end and some of these may or may not work out. But we can tell straight away that all of the correct structures have to have no rings and no pi bonds because of that formula that we used up top. So these are the different ways that I can think of to draw connections between 3 carbon atoms and 1 oxygen. A caveat that you might fall into is that you might have also drawn something in addition to these, such as you might have thought, well, I'll draw C, C, O, C. The problem with that structure is that that is identical to one that we've already drawn. That is the same thing as saying C, O, C, C, because all we would need to do is rotate around the molecule on the left to make it completely identical to the molecule on the right, because they both have the same pattern of, if we start with this carbon and call it carbon number 1, second is the oxygen, third is a carbon, third is a carbon, fourth is a carbon, fourth is a carbon. Those two are identical structures. All you need to do is rotate around to make them totally superimposable, totally identical. And so therefore, those are not going to work out as different constitutional isomers. They're not going to work as 2 different structures that we can draw for this molecule. Instead, we only need to draw one of those 2 structures, which we already drew in the upper left-hand corner there of our 4 different possible ways that we're trying out here as constitutional isomers. So constitutional isomers are defined as molecules that have the same number and type of atoms, but the connections between the atoms are different. Different atoms are connected to one another. Different branches are possible or located, where a branch is where you have a chain and then atom branching off, such as the oxygen here that I've put in red. So constitutional isomers are molecules with the same molecular formula which is what we have going on here, but different connections between atoms. There's going to be different ways that we can stitch together the atoms to make different structures. And the 2 structures we put the red X on just up top here was a place where we had a dead end where we said that those 2 molecules are identical. They are not constitutional isomers of one another. On the other hand, the structures that we drew up here are potential options for constitutional isomers that all have the molecular formula C3H8O. We're going to go through and try to determine which of those constitutional isomers are the real deal, which are ones that could actually exist versus which ones are not going to be able to exist. So what we're going to do here at step 3 is we are going to fill in our electrons that are necessary to fill the complete valence. And we're going to try to fill the octet rule for all of the carbons, nitrogens, oxygens, sulfurs, whatever atoms we have present there. So if we look back at steps 1 and 2, determine the number of valence electrons in the compound. We're going to be referring back to that quite a lot here as we get into step 3, because our total number of electrons that need to show up in the compound is equal to that number of valence electrons, which we determined to be 26 for our C3H8O. So we're going to go ahead onward with step 3 here, and I'll go ahead and write out step 3 as what we are going to do is we are going to complete the chemical structure by filling in all of the lone pair electrons and filling in all of the hydrogen atoms, which we left out so far because we're just doing skeletons of the molecules. So we're going to complete lone pair electrons, pi bonds if necessary, but we don't have any pi bonds available because we did that calculation back at step 2. So we're going to complete the lone pair electrons and the hydrogens to fill the valence for all the atoms. And remember, as we're thinking about how many electrons we have to account for our C3H8O molecule, we need to keep in mind the number of valence electrons we had to work with, which was 26, and we'll go from there. And keeping in mind that the structures that we've drawn up above here have each accounted for some of those valence electrons already, because each covalent bond consumes 2 electrons. So we're aiming for 26 electrons in total as our goal. That was what we determined at step 1 as our total number of valence electrons for this molecule. Our structures are 3 carbon atoms connected to an oxygen, carbon, oxygen, carbon, carbon. I'm just redrawing those structures that we had up top, just above here. And then we also had made a 3 carbon chain with an oxygen, and we'd made a chain that was carbon, oxygen, carbon, and carbon. And now what we're going to try to do is fill in the necessary electrons that we need in total and the necessary hydrogens. And we said that the molecular formula had 8 hydrogens, so we need to fill those in as well. In each of the covalent bonds, we've already accounted for 2 electrons. So for example, in the structure here on the upper left, we have 3 covalent bonds there, so we've already accounted for 6 of the 26 electrons out of that structure. We need to fill in an additional 20, and that will be, some of those electrons will be accounted for by the hydrogen. So I certainly suggest fill in all of the hydrogens first. So we're working in order here. We're going to fill in the hydrogens first, trying to fill the valence or the octet for all of the atoms. That's going to be our goal here because we're trying to create stable molecules. Stable molecules are going to have a complete valence or a complete octet. And once we fill in those 8 hydrogens, then we're going to use lone pair electrons to make sure that we get our total number of electrons up to 26. So let's go ahead and fill in the hydrogen atoms first here, trying to fill the octet for as many atoms as possible by using these hydrogens up first. So filling a complete octet around the carbon, we need 3 additional covalent bonds because we had 1 here to start with between the 2 carbon atoms, so we need 3 more. So that's going to be a carbon with 4 covalent bonds. So that's going to be the typical way that we will see carbon showing up in stable organic molecules. If carbon will have 4 covalent bonds to it in total. We come over to the next carbon in the chain. To make that carbon have a total of 4 covalent bonds, we need 2 more. So we'll go ahead and fill that in. Now that carbon has its complete set of 4 covalent bonds, or 8 electrons in total, since each covalent bond has 2 electrons. We come over to this carbon, fill in 2 hydrogen atoms there. Now that carbon will have our complete set of 4 covalent bonds. And we said we had 8 hydrogens in total. We count up how many we've used so far. We've used 7. So that means we need to plug 1 more in somewhere. We can never, never, never go over the octet rule for carbon. So all of our carbon atoms are fully saturated, meaning that we have filled in as many hydrogens as they can each possibly hold. So our 8th hydrogen has to go somewhere else. The only place left for it to go is to be covalently bonded to the oxygen atom. So with that, the number of electrons that we've accounted for here in green by our covalent bonds, We can count up how many electrons we used up there by counting the number of covalent bonds and multiplying it by 2, since each covalent bond has 2 electrons in total. So if we look at the number of covalent bonds, we tally that up and count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We take 11 times 2, which would be 22. Electrons are accounted for in the covalent bonds. We need 26 electrons in total. So that means that our lone pair electrons, we need to have 4 of those in total. And to fill in those 4 lone pair electrons, the goal again is to fill the valence for every atom present in the molecule. And so those lone pair electrons, to think about where we need to fill in, where we're deficient in electrons, where we need to fill in to get an octet, is going to be on the oxygen. And the oxygen, if we fill in 2 sets of lone pair electrons, so 4 electrons in total, now that oxygen has a complete octet. We're going to go through the same exercise here for the other constitutional isomers to make Lewis structures that are plausible for those. So for the next guy on the list here, our carbon, oxygen, carbon, carbon chain, we do the same ritual where we go in and first fill in the hydrogens. And we're filling in the hydrogens to fill the octet for as many of the atoms as possible. And I'm filling it in on the carbon atoms first because the carbon atoms will generally have 4 covalent bonds to them. So that's a good general principle to put down, is that carbon loves, love is a strong word, but we'll use it here, 4 covalent bonds. And that's generally going to be how you see carbon showing up when carbon is present in a stable, isolatable molecule. The only time we're going to see carbon without 4 covalent bonds is going to be in situations where that carbon is in a rather unstable situation, such as a reaction intermediate. And what we're talking about here right now are compounds that are relatively stable. So we want to fill in our 4 covalent bonds on carbon first and foremost as our main objective. And so I've gone ahead and filled those in on that structure on the upper right. And that has totaled up to 8 hydrogens in total, which accounts for all the hydrogens that we have available from our molecular formula. And if we take a look there at the number of covalent bond electrons, we're going to see that that comes out to, again, 22 that we've used up in those covalent bonds, leaving us with 4 lone pair electrons to fill in somewhere else. That somewhere else that we need to fill in is going to be there on our oxygen atom. So we'll go ahead and fill in 2 sets of lone pair electrons. And now that should indicate that in total we have 26 electrons that we have filled into this structure. We'll come down to our lower left molecule. We're going to go through the same ritual one more time, filling in the hydrogens first on the carbon, because carbon absolutely loves to have 4 covalent bonds to it. If we're making stable structures here, we need to make sure that our carbon has 4 covalent bonds all the time. So we're going to do that. Oh, and we've got a carbon here in the middle that needs 1 more bond to it to have a total of 4 bonds. So we'll go ahead and do that. And then counting up the number of hydrogens that we've used up so far, we've used up 7 and we have 8 available. So we need to find a home for the 8th hydrogen. And that home is going to be that we can bond it to the oxygen there without going over the octet. Then as our last step, we're going to go ahead and fill in the lone pair electrons that we need to have the valence filled to have a complete octet for all the atoms. So based on our covalent bonds that we've drawn in so far, if you count up those covalent bonds, you're going to see that the covalent bonds account for 22 of the valence electrons of 26 total. That leaves us with 4 electrons left, and those 4 electrons left we fill in as our lone pair electrons on the oxygen. So we do 2 pairs of electrons there, and that's going to give us the 26 electrons that we absolutely have to fill the valence for all of the atoms. We come on over to our last possible structure here, and we're going to go ahead and try to fill in our different atoms that we have available. So we have 8 hydrogens, and again, we're going to try to fill in on the carbon atoms first, because the carbon absolutely loves to have its complete octet. So I'm going ahead and filling in here. And we always kind of focus on the carbon as our center of our universe, because this is organic chemistry, and organic chemistry is defined as the chemistry of carbon. So carbon is what we put at the absolute center here. So that's one of the reasons why we're focusing on that, to draw these different Lewis structures. So we go ahead and fill in a couple of hydrogens here, and we run into a problem now, because we said we have 8 hydrogens in total in the molecular formula for this. We've used up all 8 hydrogens, but we have a carbon atom that carbon there on top that lacks an octet. It does not have a complete octet. It does not have 4 covalent bonds. And we mentioned previously that carbon loves to have 4 covalent bonds. If it is in a stable structure, if it's in a stable relationship with the atoms that it's bonded to, it is going to have 4 covalent bonds. And there's not going to be a way to put 4 covalent bonds here. So there's no way in this structure, because of the fact that we only have 8 hydrogens in total, and we already determined that we can't do any carbon-carbon double bonds to satisfy the octet, the 4 bonds needed on the carbon, or anything like that, based on the equation in step 2. There's always going to be an odd man out here. There's always going to be a carbon atom that does not have any way to have 4 covalent bonds, based on this particular skeleton that we drew, where we put the oxygen there in the middle, bonded directly to 3 carbon atoms. And so as a result of that, this particular structure is not going to be a stable, isolatable structure, because carbon, as we said, absolutely loves to have 4 covalent bonds. And so as a result, this compound represents a dead end. So what I'm going to do is just put a big X through it. This is not going to be a stable compound. It's not going to be a compound that we will be drawing as a possible constitutional isomer, because it's not something that could exist long enough in order for it to be isolated and identified. So we'll eliminate that from the list. So that's one thing to keep in mind as you're drawing out these different structures, is keep an open mind about what possibilities exist and be willing to eliminate some as you go along if you realize that there's simply no way to put 4 covalent bonds around carbon, or that there's no way to fill in all of the valence electrons without being over or under an octet. Those are going to be structures that are not suitable. So we definitely want to have carbon with 4 covalent bonds. In order for these structures to be stable, you need for them to have full valences. And in most cases, with the exception of hydrogen, a full valence equals an octet. So definitely be keeping those features in mind as you think about what possibilities are reasonable. So our lone pairs here we're showing as dots. Our lines are represented as our covalent bonds. So that's our overview of drawing Lewis structures, one of the ways that we go about showing structures for organic molecules. And it'll be one way that we can show the different constitutional isomers that are possible, the different ways of arranging atoms based on the molecular formula that we are given for those.